Okay, so we are going to talk about, like I said, kind of the introductory type stuff. So we'll try to hit here in this lecture things about measurements. And there's really no notes. I'm just gonna, like I said, kind of just do it off the top of my head here and see if I remember. Measurements, we'll hit hopefully sig figs. I am writing this all, remember, maybe to cover all this stuff. Scientific notation. We'll talk about sig figs and calculations. We'll do some talk about conversion factors and some dimensional analysis. Temperature conversions. And we'll finish up hopefully with some density. I think that's most of all that kind of topics. Okay, so let's start with really the first thing there, which is measurements. And there's really two types of measurements that we sort of come across. One is sort of qualitative, and one is sort of quantitative. Qualitatives really just sort of general observations. General observations, you know, gas developed, solid developed, thing turned purple, those type of things. Quantitative is really about measurements and values. And when we do take quantitative measurements, it's really important that we record not only the number, but also the units, right? So we always want to record the number and the units. And that's really important because obviously if I just said, hey, I have 100, really have no idea what that means. I could have $100, which would be great. I could have 100 pennies, still not too bad. Or I could have 100 pencils, which could be good as well, I suppose, depending on your perspective. So you always want to make sure that your numbers associated with the units, again, like I said, pennies are different than say dollars or something like that. It gives the sort of person that's looking at the number, obviously an understanding of what that number represents and sort of what scale you're talking about. As you may remember, there really are sort of two basic branches of units. There is really the English sort of brand of units, which we use here in the United States. And then pretty much everybody else pretty much uses the metric system for the most part. And that's what most likely everybody sort of uses. So it is sort of problematic, obviously, as everybody sort of deals with each other, that if people are using different units, there could obviously be some mistakes that could happen. So like in 1960, they had a conference on units, sounds like fun. And they came up with sort of a unified sort of version of units that you sometimes hear about in chemistry, which is sometimes referred to as the SI units. And the SI units is the International System of Units. It frankly is based off of the metric system pretty much, is what it is. But it's usually the units that we use a lot in chemistry, and really, like I said, sort of the metric system is really what it is. So it's really important to do these sort of units. The metric system has a lot of sort of prefixes that are used, right? You know, things like prefixes like centi, right? Kilo, and so forth. And those are used to basically represent or sort of change the meaning of those numbers, as we could have really large numbers or small numbers. And sometimes you may see something like, you know, kilo is 10 to the 3, for example, as a conversion. And I will say, when you see those type of things, sometimes it's very common that people will do the conversion wrong. When you see something like that, that kilo is like 10 to the -3, centi 10 to the -2, whatever it may be, what that means is that's how much there is in the base unit to one of the prefix units. So for example, what that would mean is and one of the prefix units like kilograms, there would be 10 to the 3 grams. And it's very common. People will always sort of reverse those and kind of do it the opposite way. It doesn't really matter the unit, the base unit. You could do liters too, and 1 kiloliter, there would be 10 to the 3 liters. So it's a very common thing, you know, when people look at it, you know, for example, I'm getting old, but we'll do like 10 to the minus 9. Like nano is 10 to the minus 9. You'll sometimes see that. And again, what that means is if I had 1 nanometer, there would be 10 to the minus 9 meters. And by the way, the 10 to the minus 9, the 10 to the 3, that is it written in scientific notation. It's basically 1 times 10 to the 3, 1 times 10 to the minus 9. So you want to be careful with when you use these sort of prefixes, which we do use a lot in chemistry, obviously, and we will use, for example, nano a lot in the next chapter, and centi and kilo a lot throughout this stuff, that you do get those sort of conversions correctly and not sort of do it backwards. Any questions on that there? So when we look at these things and we talk about numbers, we can have really large numbers, right? And we oftentimes will use scientific notation to help us sort of make sure we don't maybe lose zeros along the way. And scientific notation is written in the form of n times 10 to the n. And this n is a number between 1 and 10. So it's not 10, it's not 20, it's not 100, it's not less than 1. It needs to be a number between 1 and 10 times 10 to the little number up here, which could be either a positive or negative number, depending really on which way you move the decimal point to get to a number between 1 and 10. So for example, if I had 0.0000325 and I wanted to write this in scientific notation, I do need to move the decimal place 1 place, 2 places, 3 places, 4 places, and 5 places to the right. That gives me a number like 3 point something, right? Which is obviously a number between 1 and 10. And that gives a 3.250 times 10. I lost track. 1, 2, 3, 4, and 5 minus 5. In terms of what it should be in scientific notation. Obviously, if I had a larger number like 4250000, although there is no decimal point written here, we would kind of assume it's at the end. And in this case, we would need to go 1, 2, 3, 4, 5, and 6 places to the left. And that will give us 4.25 times 10 to the 6. In this case, when we move the decimal place to the right, we end up with a negative exponent, right? And when we move it to the left, we end up with a positive one. Or you could just remember a large number should have a positive exponent. A small number should have a negative exponent when you do that. We'll talk why. Obviously, I cut out some zeros and kept some zeros in just a second, but there is a reason, obviously, why we did that. Any questions on that? So if you obviously have a number in scientific notation, you do the opposite. So -5 would mean we would go 5 places to the left. +6 means we would go 6 places to the right, and obviously add the appropriate amount of zeros that is necessary to do so. When we write a number, does it always have to be in scientific notation? The answer is no, it does not. I don't really care. As long as you have the right number of significant figures, which we'll talk about in just a second, you can do it, or you don't have to do it. Obviously, if the instructions say to write in scientific notation, you should write in scientific notation. There is a time, though, that it can happen that the only way to write the correct answer is to put it in scientific notation. And that is because when you write a number in scientific notation, any number that comes before the times 10 part, any of those numbers, they're always significant. So you can really sort of write a number as however many significant figures you want in scientific notation, so you can kind of control it. So that's why sometimes the only way you can kind of get to the right number of sig figs is to use scientific notation. More importantly, though, is other than writing it in scientific notation and knowing how to do that, is to know how to properly punch it into your calculator in scientific notation. So for example, on your calculator, you should have an exponent button. And on most people's calculators, it is either an EE button, it is an EXP button, or if you have some of the newer calculators, you might actually have a times 10 to the n button. And I'm sorry if you have that calculator. No, I'm just kidding. It's okay. But these are really your exponent buttons. And whenever you type something in scientific notation into your calculator, you want to make sure that you are doing it correctly. So for example, if we were going to take 6.25 times 10 to the minus 3, and we wanted to really punch that into our calculator correctly, we would take 6.25 and you would hit your exponent button. And we're going to talk about these two first. We'll come back and talk about what to do with this button here, if you happen to have that button. When you hit the exponent button, I am not hitting the multiplication button or anything like that. I'm just simply hitting the exponent button. On most people's calculators, that will put a 6.25 in an E. It may do like a 6.25 and maybe pop up a couple of zeros, something of that nature, or maybe a little times 10 might be written underneath it. But those are typically the two things. When you hit the exponent button, that represents this part of the number. That means you do not need to hit the multiplication button. You do not need to hit inverse log or anything like that, because that is incorrect. What's left is you have -3 left to do. That brings us to another couple of important buttons. That is your negative buttons. That looks like that, or it looks like this. It is not the subtract button. Yeah, so on your calculator, you should have one of those two buttons as well. You would then hit this and then 3, and that will put a -3 there. That will change this to like a -3. And that is really the correct way to punch a number into your calculator scientific notation. You should not be using a multiplication button. You definitely should not be using like the second log button or anything like that. You typically will find yourself knowing you are punching this in incorrectly in your calculator, because the front part of the number will look good, but your exponent part will be like off by a number or something like that. And that's usually an indication that you probably punched it in incorrectly. Now, while we have it, if you do have this button here, and typically those are on some of the newer calculators that have, a lot of times they're like two-toned. They have like two different colors. If you do have that button, the only difference that you need to do is actually you need to put parentheses around every number that you put in scientific notation. Because of the way the calculator most likely is programmed, you would have to open a parentheses if you have this button here. You would then need to hit 6.25. You would then hit that button. And what will happen is on your calculator, it looks something like this. It'll put a times 10, and you'll have like a little blinking cursor up there on top. And then you could kind of do the rest of it. You then would hit your negative button and your 3. And when you do that, you will have 6.25 times 10 to the -3. And then you will have a little blinking cursor up there on top next to it. Usually if you have this button, you also have what I call the will on your calculator, like a little will button type of thing next to it or somewhere on your calculator. What you actually need to do on most of these calculators is like hit this side of the will. And what that will do is bring your cursor back down to a regular size cursor. And at that point, you could actually close the parentheses. And then, so you got to kind of do this move here, hit that, and then close the parentheses. And then that will give you your number in scientific notation. So I find that if you do not do that, you don't use parentheses on that calculator, it will do the math wrong. And I also find that a lot of those calculators, if you don't bring the cursor back down to a real size one, it will also give you an error or something like that. So that is really more important probably than knowing how to write it in scientific notation. is to know how to punch it into your calculator. Any questions on that? Again, if you're not sure where your exponent button is, just bring it up and we'll find it together at some point if you need to. But those are probably the three most common sort of exponent type buttons. If you have one of these first two, you don't have to worry about parentheses. You could just roll numbers and hit the button and everything will work out okay. So let's just try one here just to make sure everybody can punch it in correctly. Let's do 3.25 times 10 to the -5, and we'll divide it by 1.6 times 10 to the 22. And then let's do 4.6 times 10 to the -11 times 3.3 times 10 to the, we'll do 5. All right, I'll do it as well since I made it up. Let's see what we do. Okay, let's take a look. So if we were to punch the first one in, once again, 3.25, you hit your exponent button. You would hit your negative button. You would then hit 5. You would hit your divide button. You would do 1.6 exponent button and 22 as it's positive and hit the equals button. If you do all that good stuff there, you get something like 2.03125 times 10 to the -27. Now, a couple of things when you get this number that people sometimes leave off. For example, on my calculator, this is the actual what it shows, E minus 27. So that's what it shows on my calculator. And sometimes on people's calculator, this exponent part is far to the right, and people oftentimes forget to actually write it. So you don't want to forget to write it. You also, when you write a number in scientific notation, you should not use the E. You should use times 10 when you actually write it out as a value and number. A reminder that you will not always maybe given the right sig figs in terms of your calculator. So if we were to clean this up, and we'll talk more about this in just a second, it should kind of clean up to something like that. If we do the next one, you would punch it in the same way. And if we did that, we would take 4.6 exponent button -11. We would times it by 3.3 exponent button and 5. And on my calculator, I get 0.00001518, which if we wanted to turn into scientific notation, we would go 1, 2, 3, 4, and 5 and give us 1.5 times 10 to the -5, as that's a small number. So again, it may not give it to you in scientific notation. You may have to turn it into scientific notation unless your calculator is programmed, obviously, to do that, which on most calculators, you can program it to give your answer in scientific notation as well. Question on how to properly punch it into your calculator. Okay. So again, if you're not sure, or you find yourself again looking at an answer and it's just slightly off in the exponent part, it's usually how you're punching it in. That's the problem. Okay. So we sort of diverged into scientific notation here. Let's go a little bit back to measurements and talk about proper measurements. Whenever you take a measurement, there's always some degree of uncertainty in it. And the degree of uncertainty in a measurement depends really on the equipment that you use as to how good or bad you might be able to make it. So for example, if we look at something, we'll say these are centimeters. And we go to here. All right, so let's say we wanted to figure out, the proper measurement here. The first thing that you really want to do is look at the scale of the equipment that you're using. And there usually will always be, in most cases, two types of markings, sometimes referred to as smaller markings and larger markings. In this case here, our larger marking is 1 and here is 2. So our large markings here is 1 centimeter, basically the difference between those. When we count how many of the smaller markings are between the large markings, we always want to start past the last large marking. So this would be 1, this would be 2, that would be 3, 4, 5, 6, 7, 8, 9, and 10, basically coming across there. So we want to count how many of the small markings there are. So the small markings, there are 10 of them, right? And that means that each of the small markings represents how much on this scale? Represents 0.1 of a centimeter, right? 0.1 centimeter. This would be basically 1.1, right? 1.2, 1.3, 1.4, 1.5, 1.6, and so forth, all the way up to 2. So when we take this measurement, there should always be numbers that pretty much no matter who takes a look at it, everybody should agree upon. And if everybody looks at this, they should agree that my arrow is at least 1.3. It's clearly not 1.4, but it is at least 1.3. And you should record all these numbers. These are sometimes referred to as all the certain numbers. Now, when we look at this arrow, we could clearly see it is not exactly 1.3. It's not exactly 1.4. So this is really where the estimation comes into play, or the degree really of uncertainty comes into play. Now, I may look at that and go, I think it looks like halfway between those 2 points. So that sounds good. And I may record a 5. And obviously the units, which would be centimeters. Now, somebody else may look at it and go, I think it's kind of a little before half. Maybe it's like a 4, or maybe it's like a 6 or something like that. And this number here is what is sometimes referred to as the first uncertain number. And whenever you basically take a measurement, you should always record all the certain numbers plus the first uncertain number. And really, that is what is referred to as significant figures. That's basically what significant figures are. Is in a measurement, you take all the certain numbers plus the first uncertain number, and that is how many significant figures there would be. That means that this particular measurement has how many significant figures? Has 3 significant figures in this case, yeah. Usually speaking, it's like plus or minus 1 of like the uncertain number, right? So, we're saying in this case, that plus or minus 1 of the uncertain number usually. So we're saying, I think it's like 1.35, but maybe it's like 1.34, maybe it's 1.36. It's somewhere in that ballpark. That is where the uncertainty basically lies. Now, it's really important that you always look at the scale that you're using, be it a ruler like this, for example, be it a graduated cylinder that has some measurements on it. So, for example, if we had something like this. Do one more there. So we'll call this 20. We'll call this guy up here 30 milliliters. We'll call this like a graduated cylinder-ish. We'll throw some liquid in there. The classic blue liquid. All right, so when we read a volume, for example, of a liquid, like in a glass container, first off, right, we always will see this kind of curvature of the liquid, right? That is what is known as the meniscus. It is curved because, as we will learn, the attractive forces between the liquid and the glass are stronger than the attractive forces between the liquid and itself. So what you get at the edge when they come in contact with each other is they start to rise because stronger attraction kind of rises up there. That is why in this particular case, we should always read from the bottom of the meniscus, right? And that's because that is really where the true volume is. The outsides are really just up because of the attractive forces. The real volume is, if there wasn't that attractive force, it would drop back down on the sides, and it would be really where the bottom of the meniscus would be. Obviously, if it went the opposite way, which, by the way, Mercury goes the opposite way, you would read from the top of the meniscus in something like Mercury. It's kind of the rare example, but we don't usually use too much with Mercury anymore. But Mercury actually is more attracted to itself than the container. So it actually comes in on itself and makes kind of the opposite meniscus. But pretty much 99.9 times out of 100, that is what your meniscus is going to look like. And you want to look at it from the bottom. As we look at our large scaling on this guy here, we have 20 on the bottom there, 30 on the top. That is 10 milliliters in this case. Once again, if we count the number of lines between them, starting with the one past the big marking. So that's 1, that is 2, that is 3, that is 4, that is 5, that is 6, that is 7, that is 8, that is 9, and that is 10. That is 10 markings between 10 milliliters. That means each small marking is 1 milliliter, right? And that means that this is 21, 22, 23, 24, 25, 26, 27, 28, and 29. So once again, when we take our reading here, we can see that it is at least 24, and that is what we should record here. That is definitely our certain numbers, which is 24. Once again, here it is not exactly at 24. We go from the bottom of the meniscus. Maybe you don't feel it's exactly half. So we would record maybe 4 milliliters. This would be our certain numbers. This would be our uncertain number. And in this case, this would have how many significant figures? It would have 3 significant figures as well. Yes, all those would be significant in this particular case. In most cases, you could take the reading to one more place to the right of the smallest marking. In this case, our smallest marking was 1. We were able to take the reading to one more place to the right of the smallest marking. Here, our smallest marking was 0.1. We were able to go one more place to the right of the smallest marking. You can sometimes calculate the how far you could take a reading by taking the smallest marking and dividing by 2. If you take smallest marking divided by 2, in this case, you get 0.05 centimeters, which basically says you could take it to the second decimal place like we did at this reading. If you come over here, take the smallest marking, which is 1 divided by 2, 0.5 milliliters, you could take it to the first decimal place. So if you're not sure how far you should take it, you typically take the smallest marking and divide it by 2, and that will kind of tell you how far you can take the reading to. Now, it's not always the case. So for example, if we had something if we had like a graduated cylinder, sort of like this deal, and again, we'll put it, we'll go here. So when we look at this markings, once again here, we do have the large marking between 20 and 30. So that is going to be 10 milliliters. Now, when we look at the smallest markings in this case, that is 1, that is 2, that is 3, that is 4, and that is 5 in this case. That means that each of the smallest markings in this case represents how much? 2 milliliters. Yes. That would be 22 sounds better. 24, there we go, 26 and 28. Thanks. So now actually we're between 24 and 22. So what comes between those two is 23 milliliters, right? That is the best that you could do in that situation based on the scale. There's no good way to know where 22 stops, right, in that space, and where 23 begins and ends. So there's no real good way to space it out. So the best that you could do in this case would be to record 23. By the way, how many significant figures would that have then? It would be 2, right? This 2 here, that would be our certain number. That would be our uncertain number. And this would have 2 significant figures, right? And we also could do the same thing as we just talked about. We could take the smallest marking, divided by 2 is 1 milliliter, is how far we really can take that reading to. Any questions on that there? Now, it's also really important and a very common mistake that people make when they do take measurements. Let's go back to this guy here. We'll edit out that there. And let's just say we were going to measure like this guy, like dead on there. All right, so if we were going to measure this guy here, what here should we record? Is this 1.3 centimeters? Is this 1.30 centimeters? Is this 1.3000 centimeters? I'm just going to eliminate that. Remember, putting extra zeros doesn't make it more scientific-y. Yeah, so to make it look better. So is there really a difference between these two values that you record? Well, let's see if there is a difference. So let's take a look first off at this first number. If I then asked you how many significant figures would this number have, how many significant figures does it have? It does have 2 significant figures, right? The uncertain number is which number? It is the 3 here, right? That is our uncertain number. So basically, when you write 1.3, what you're saying in this case is, I think it is perhaps 1.3 centimeters, but maybe it's like 1.4, maybe it's 1.2 centimeters. We could clearly see from the picture that it is nowhere near those numbers, right? So it's nowhere near 1.4, right? Nowhere near 1.2. That's a pretty big range of uncertainty that you have, right? Now, when I look at this number, how many significant figures does this number have? It does have 3 significant figures. The uncertain number is it is the 0 here, right? And that is our uncertain number. And basically what this measurement says is, I think it's 1.30 centimeters, but maybe it's like 1.31, maybe it's like 1.29. And looking at where it actually is sitting based on our scale, that is really the correct measurement, right? So sometimes people think it's on the nose. It doesn't really matter if I loft off a 0 or something like that, but it does, right? You pretty much, when you dump the 0 over here, you made this a pretty crappy measurement. Yes, there's a lot of uncertainty here, and you would not want to record it. You would want to go based off of its scaling there, and that's a much better measurement, right? And there's a lot less uncertainty there than there is in the first one. Any questions on that? So it's really important not to just get rid of zeros and stuff like that. If you hit right on a nose like we do here, and you have the ability based on that particular piece of equipment to take it to that 90 decimal places, you should put the 0 there to maintain the right number of significant figures. Otherwise, you're making your measurement pretty bad in that particular case. Any questions on any of that there? So when you do take measurements, you should take it to the proper number of digits based on the scaling. By the way, if you use anything that is a digital display, like it digitally gives you the numbers, like a balance, for example, you should always record all the numbers. They are there for a reason, because they're important. And that's also a very common mistake that people make. They just like, it's like 52.35. 52 seems good. And again, you're going to make that number a lot worse of a measurement than it should be. Any questions on measurements there? Speaking of measurements, we oftentimes talk about 2 types of numbers, accuracy and precision. And when we talk about accuracy and precision, they do mean 2 different things. Accuracy is how close a set of numbers are. Sorry, how close a set of I say it right. Hang on. How close a number is to the true value. There we go. Precision, on the other hand, is how close a set of numbers are to one another. So the classic example is like you're throwing darts at a bullseye, right? The goal is to hit the bullseye. So you throw your darts and you throw it and you hit here, perhaps you miss the board. Happens, right? Am I accurate here? No. Am I precise? I am neither, right? So you go, all right, well, we'll do like a double or nothing. That's like my warm-up throw. It's okay. I'm really good at this. So you take your darts and you throw them again. Am I accurate? No. Am I precise? Yes, I'm precisely not accurate. Yes. And that happens a lot, right? You could do the wrong experiment 5 times and do it wrong every single time, but you're very good at doing it wrong every single time and you'll get the same number, right? So you could be very precisely bad at something, right? And do it the same way every single time. But you're not very accurate in terms of what you're looking for. All right, so you go triple or nothing, which is usually the time where you should not take that bet because you shouldn't bet in general, but you shouldn't take that bet because you're probably being hustled. And they throw the darts and they go boom, boom, boom. Am I accurate? I am accurate, right? I hit the bullseye. I'm pretty precise, right? And when we do take measurements and stuff like that, we do want to look and try to be both accurate, right, and precise. And that's why oftentimes, right, we do a number of different trials and experiments, right, to see how reproducible, how repeatable an experiment is. And that's looking at things like precision. And there's also correct numbers in a sense, right? So we look at accuracy and that helps us understand whether or not something is accurate or not. We oftentimes, in terms of accuracy, we'll look at what is sometimes referred to as percent error. And that is typically your experimental value minus the true value divided by the true value times 100%. And a lot of times you could either take the absolute value of that or not. If you take the absolute value, it'll just be a number. If you don't take the absolute value, then you'll either have a minus or a positive number. Positive just means you're a little bit above the true value, right? And negative means you're kind of below the true value is typically what that means. For precision, there's several different ways you could look at. You could look at percent deviation. Like you look at standard deviation is a lot of times, sometimes what we look at. And standard deviation is the square root of the sum of your experimental value minus your average squared divided by n minus 1. We don't really calculate too much standard deviation here, but that's, sort of how you do it. And that's a lot of times what we look at, or percent standard deviation or percent deviation is something that we look at in terms of precision. Any questions on that there? Okay, so talk about measurements. Let's talk a little bit about significant figures and counting significant figures to make sure everybody's on the right page. So the first rule for significant figures is any non-zero is significant. So if we had 1, 2, 3, 4, very creative numbering there. We always start counting left to right. So we would start counting here. It's a non-zero. We always start counting at the very first non-zero. So all those are non-zeros. So this guy would have 4 significant figures. The second one involves zeros, and that is usually what gives people some trouble. We could have what is sometimes referred to as leading zeros. And those are not significant. So 0.000123, all of these are not significant until we hit the very first non-zero number. And that's when we start counting. And then the rest of them are non-zero. So that's going to be 3 significant figures for this guy. The next type of zeros are sometimes referred to as trap zeros or captive zeros. And these zeros are significant. And those are zeros really between 2 non-zero numbers. So if you had 4004, we would start counting here as that's significant. These guys are trapped, so they're significant. And that guy at the end is significant. So this guy would have 4 significant figures. Any question on that so far? Now, it is the last type of zero that usually gives people the hardest time, and that's the trailing zeros. And they may or may not be significant. And what determines whether or not they are significant is there a decimal point in the number? So basically, they will become significant if there is a decimal point in the number. Now, that decimal point does not need to be right next to those zeros. It just needs to be in the number, anywhere in there, and it will be significant. So if we had something like 400, and if this was a measurement, this would have how many significant figures? It would actually have just one, which would be this one. These zeros at the end are not significant, as there's no decimal point actually written. This would be one significant figure. Now, when we look at something like, say, 400, and I put a decimal point there, this would now have 3 significant figures. This is significant. These are significant because of the decimal point there. If I have 0.0004003003000, how many significant figures this has? If this was a measurement, I have no idea. I'm just writing numbers, but let's see if we can figure it out here together. So we're going to blank the screen and then we're going to come back. All right. So starting here, that is a 0. We would not count, right? We're still not counting. This should be the very first number that we start counting, as that's the first non-zero. That is significant. These zeros are trapped, so they are significant. So that's 3. That is significant. That's 4. These are trapped. So that's what, 5, 6. That is significant because it is a 3. Now we have these zeros at the end. Are they significant? They are significant because way back over here, there's a decimal point in the number. Does not need to be sitting next to them. So that is, I lost track, but I think you're right there. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 significant figures. Yeah. Any questions on that there? Okay. Now you should, when we talk about calculations and significant figures, there's really kind of 2 types of calculations we do. We typically will multiply and divide, or we will add and subtract. Basically, are our 2 sort of categories of stuff that we do. When you multiply or divide, your answer should have the same number of significant figures as the number with the least number of significant figures. So if you add or divide, whichever number in that calculation has the least number of significant figures, that is how many significant figures your answer should end with. So if I did 32.5 times 10.060, the answer should have how many significant figures here? It should have 3. That has 3 sig figs. This guy has 5 sig figs. Our answer should end up with 3 sig figs, right? Now, when we add and subtract, it is a little bit different. Your answer should have the same number of decimal places as the number with the least number of decimal places. So if I take 1.256 and add it to 3.20 and add it to 4.1, I'm going to try it without the calculator. That's a 6, that's a 5. I think that's a 5. That's an 8, I think. Yeah. So we end up with something like this. We are looking here again, not at significant figures, but at decimal places. This guy has 3, this guy has 2, and this guy has 1 decimal place, which means we should take the answer here, right? That means we should also look at the number next to it, and it's above 5, right? Or 5 and above. So we should round up, right? And we should end up with 8.6. 8.6 has 1 decimal place, right? How many significant figures? 2. And that's important to keep that difference between those two, because you may need to do something with that number. Any questions on that there? Now, sometimes you do multiple sort of calculations together or processes together. Usually you want to keep track of all your calculations and the sig figs, and you really usually do not want to round to the very end, kind of clean it up at the end, but you should keep track of it. Sometimes people will keep guard digits and put little lines or whatever, but you can just take it to a few more digits that you need. And then at the end, you should round it to the correct number of significant figures. If we did a sort of combination of multiple things together, like I said, you would want to kind of keep track of it. So why don't we just take a look at one here? Let's just say we were going to take 3.5 times 1.2. We'll divide it by 1246. Then we'll add it to 1.32. All right, see what you come up with. I will as well, because I'm not even sure what we got going on here. Let's see. Okay, so let's just kind of do the math part first. So we go in our calculator, a little 33.5 times 1.2 divided by 1246. If we kind of got the answer for the left part here, 0.032263242 plus 1.32. We add 1.32 to it. We end up with 1.352263242, I think. All right. So we obviously don't want to give that answer, and you should not do that, by the way. Yeah. So if you find yourself giving sig figs and you're wrapping around the page with how many there are, and I've seen it done before, by the way, on exams and quizzes, you should not be doing that. So if we sort of dissect what we should do here, the first thing that you would obviously do in this case is the parentheses part, right? So that is multiplication, which means we are looking at significant figures here. And that is basically 3 sig figs, right, for this guy, 2 sig figs for this guy, which means technically when we get the answer for the top part, it should have 2 significant figures, right? The next thing that we would do is take that number and divide it by the bottom number, which is also looking at significant figures. So we basically would be taking a number that has 2 significant figures and dividing it by a number that has 4 significant figures, which means when we're done with the left-hand side here, we technically should have how many significant figures? 2, which technically takes us to here, right? That means, technically speaking, we are taking 0.032 plus 1.32. That means that what we are going to do next is add. And when we add, we're looking at decimal places, right? And the first number has 3 decimal places. Second number has 2 decimal places, which means our answer should have how many decimal places? 2, which means that is what our answer should be, right? 1.35 has 2 decimal places, but how many significant figures? 3 significant figures, yeah. So that's really what you want to do when you kind of combine all this together in multiple calculations. You want to really keep track of it. Personally, I just go with my calculator and the whole number, and I personally do not round to the end and kind of clean it up at the end in most cases. But if you do want to kind of round along the way, or if you get an answer and you need to take it and do another part with it, I would recommend taking it to a few more digits than you need based on sig fig rules, and then at the end, clean it up. The problem with strictly rounding after every single step is you will move yourself further and further away from the right answer because you're basically making the measurement worse, right? Every time you round it. We round to the lowest sig figs, lowest decimal places, because frankly, those are your worst measurements, right? And your worst sort of measurements in a group of numbers is the one that has the least number of sig figs, the least number of decimal places. And that is what limits how good or bad your measurement is. And that's why we go to those. But if you do it along the way in the calculation, you're eliminating more and more along the way, and you will find yourself moving further and further away from the right question answer. Any questions on that there? Speaking of rounding here, just to finish up on this topic, normal rules apply, right? Less than 5, we kind of drop the numbers. More than we do round up. We want to be careful when we round. So for example, if I had 13,333 and I wanted 2 sig figs, what should the answer be? So is 13,000, how many sig figs do both of these numbers have? This number has how many significant figures? 2. This number has 2 as well. Those zeros at the end are not significant because I did not put a decimal point. They both have 2 significant figures, right? But there is a really big difference in the meaning of those 2 values. If I owed you $13,333 and said, hey, I'm going to pay you 2 significant figures, here's $13. I'm probably not going to make it out of the room, I imagine. Maybe I will. You look friendly, but maybe we'll be in some trouble, right? There's a very big difference between the meaning of 13, right, and 13,333. So you never want to do crazy rounding, I like to call it, extreme rounding, where you change the meaning of the number in an effort to get the right number of significant figures. It happens a lot because people are focused on trying to get the right sig figs that they do the extreme rounding and they end up with, obviously, a number doesn't make sense. This is 13,000, which is pretty close to 13,333. Maybe I get the $333 teacher discount, right? You know, it's pretty much the same deal. You also could, right, if you wanted to, do a little scientific notation, right? 1.3 times 10 to the 1, 2, 3, 4. That would have 2 significant figures, right? Again, the numbers before the times 10 part are significant. Question on that. By the way, with that, that is why when we had something like this, 0.00200, and we had something like 42,500, when we turn this into scientific notation, 1, 2, 3, that would be 2.00 times 10 to the minus 3. That is because this number has how many significant figures? It does have 3, these 3 right here. When I turn it into scientific notation, I should still have the same number of significant figures. You should not lose any going back and forth. This guy has only 3 significant figures. So when we turn it 1, 2, 3, 4 significant figure, 4 decimal places, 4.25 times 10 to the 4, we drop the zeros. So now that they both have 3 significant figures. So you do not want to lose significant figures as you go from scientific notation to decimal place. Any questions on that? Okay, we have a few more topics to cover to make sure, again, everybody's on the same page. So we've talked about measurements. We talked about how to properly take measurements. We talked about significant figures in calculation. Let's talk a little bit about 2 types of numbers that we come across, and that is measured numbers versus exact numbers. So measured numbers obviously is a result of some type of measurement. So, you know, if we had something like we had before, 1.30 centimeters, we know that this has 3 significant figures, as we talked about, because it was a measurement. Exact numbers are a little bit different. Exact numbers are really found in 1 of 2 situations usually. It is essentially something that's either counted or something that's a sort of definition, or an equality, like 1 foot is 12 inches, you know, 1 inch is 2.54 centimeters, something like that. So, you know, if I had, for example, the classic example of most textbooks, like 5 apples sitting on the table, I'm not going to do any type of experiment to figure out how many apples I have. I'm just going to simply count them. So that's considered an exact number. And really anything like 1 foot is equal to 12 inches, or 1 inch is like 2.54 centimeters exactly, is considered an exact number. Exact numbers can have as many sig figs as you like. So really what happens when we do come across, for example, an exact number in a calculation is we ignore it. And we ignore it because it could have as many sig figs as you want. Somebody might use 3, somebody might use 4. So there's a lot of variety that could happen in that situation. So whenever you're doing a calculation that involves an exact number, and in most cases, it's going to be probably like one of these type of definition type of things, you do ignore it. And in a lot of cases, if you're just simply doing a conversion, usually the first number you start with, a lot of times will have the right sig figs as your answer, because when you do conversions, you usually just multiplying and dividing. So usually will have the right number of significant figures. So if you come across an exact number in a calculation, you should ignore it, and you should look at all the other numbers that are not exact numbers and look at them in terms of their significant figures. Now, speaking of sort of conversions, let's talk a little bit about temperature and the 3 major temperature scales that we come across. There is degrees Celsius, there's degrees Fahrenheit, and there is K, which is Kelvin. One of the main difference, as you can see right here, is degrees Celsius, degrees Fahrenheit. They do the degree symbol, no degree symbol here. So it is just Kelvin. So 273 Kelvin is how you would say it. You would not say 273 degrees Kelvin or anything like that. So no degrees. Converting between these are important, but really for the most part in chemistry, that is your temperature value for the most part. Pretty much everybody needs to be in Kelvin, and most chemistry type of formulas that involves temperature. There's really a few that will use degrees Celsius. Specific heat will use degrees Celsius, but we don't do that anymore in this class, so you don't have to worry too much about that. But pretty much everybody will do Kelvin. To convert the temperature in Fahrenheit will equal 1.8 the temperature in Celsius plus a 32. If you want the temperature in Celsius, that would be the temperature in Fahrenheit minus 32 divided by 1.8. So those are the ways that you can convert between degrees Celsius and degrees Fahrenheit. The 1.8 sometimes uses 1.8, 1.80. It's the same as 9/5, which you might have learned is fraction version of it. Is also the same sort of conversion that you can use here. I would say probably in most cases, not going to see too much of these conversions, maybe in some early chapters, but really not too much. The conversion in terms of temperature that we see the most is, frankly, degrees Celsius to Kelvin. And that is because in most times our thermometers are in degrees Celsius. So we take measurements in degrees Celsius and then has to convert it to Kelvin. So to do that, the temperature in Kelvin is equal to the temperature in Celsius plus a 273. The correct number is really 273.15. If you like to use that number, you can. Most people drop the 0.15 because, frankly, it gets rounded off in most cases anyways. But if you want to use the whole number, you can. But 273 is what you want to do there. If you want the Celsius and you got the Kelvin, that's going to be Kelvin minus a 273. And I would say probably in most cases, these are the ones we're going to use. And in most cases, it's going to be this guy on top is the one that we're going to use the most here. Now, you do need to know these formulas, yes. So a reminder that formulas will not be provided to you. So you do need to know formulas. Constants and some conversions will be provided for you, but any type of formulas you do need to know as we go through the different sort of chapters. Now, if you want to get to Kelvin and you got like Fahrenheit, you got to go from Fahrenheit to Celsius, Celsius to Kelvin, and vice versa. If you got Kelvin, want to get down to Fahrenheit, you got to kind of go through those type of calculations. Now, let's try a couple here. Let's say we had 41 degrees Celsius and we wanted degrees Fahrenheit. And let's say we had, we'll go with 75.5 degrees Celsius. And we want Kelvin. So once you do those two conversions, see what you get. Okay, let's take a look. We'll start with the top one here. So we want to go to Fahrenheit, and we have Celsius. So our temperature in Fahrenheit will equal 1.8 our temperature in Celsius plus a 32. And if we do that, 1.8 times 41 plus 32 can give us 105.8 degrees Fahrenheit. This should end up at about 106 degrees Fahrenheit. And I'll tell you why that is in a second. When we are doing temperature conversions, and only with temperature conversions does this apply, we do not follow strict significant figure rules here. And that's because there's a lot of variation in terms of how you could do this conversion. Some people use 9/5, which is kind of like a fraction, an exact number. People use 1.8, 1.80. So there's a lot of variation. So if you are simply just doing a conversion between one temperature scale to the next, you should make your converted value look like your original value. And what that means is, in our case here, our original value was 41, a whole number. We should take our converted temperature to a whole number. If our original value was 2 decimal places, we should take our converted value to 2 decimal places. So that is just specific for temperature to temperature conversion, is what we follow those rules. If we did our guy on the bottom here, our temperature in Kelvin would be 75.5 plus a 273. And in this case, 75.5 plus a 273, going to give us 348.5 Kelvin. Here we would leave actually the decimal because we had 1 decimal place there. We take our converted number to 1 decimal place as well. So that is the general rule for temperature conversions. Whatever the original number looked like, make your converted temperature rule value to that. Everything else is not just a temperature to temperature conversion. You follow obviously the significant figures rules that we talked about previously. Any questions on temperature conversion? Okay. So speaking of conversions, that takes us to the next really topic we want to talk about, which is conversion factors and dimensional analysis. So really conversion factors are just fractions that come from what is known as an equality, right? An equality are really 2 values that represent the same amount of something, but they're on different units. Like if we did have 1 foot is 12 inches. They both represent the same amount of length, but they are on different unit scales, and that is an equality. From any equality, you could write 2 conversion factors. You could write, for example, 1 foot over 12 inches, or 12 inches is 1 foot. You would not use both of these conversion factors in a calculation. You would use obviously whichever one that you need. So for example, if I had 453.6 inches and I want to know how many feet that would be, the way that we set this up is we do dimensional analysis, which is the way that you should do most of your calculations in chemistry. Dimensional analysis really is multiplying and dividing, and it is an approach that we use where we basically have a unit that we want to get rid of. We use a conversion factor that has that unit in it, and that will allow us to convert to the next unit. In this case, what we are doing mathematically is multiplying whatever's on top, coming back and dividing by whatever's on the bottom here. In this case, we would divide unit A divided by unit A equals 1, basically, like you take 2 divided by 2. They cancel each other out. That leaves us unit B that we are looking for in this just generic example here. So if we were going to do this, and when we do dimensional analysis and we want to cancel out units, it's always opposites cancel, right? Pretty much math. If you want to cancel something, you do the opposite approach. So if the unit you want to get rid of is on top, you need to put the same unit on the bottom. If the unit you want to get rid of, it's on the bottom, you got to put that same unit up on top. So opposites always cancel each other out. So in this case, we would take 453.6 inches. Inches is what we want to get rid of, although it is not really written as a fraction. It's basically over 1, which means the units of inches are up on top, which means when we look at our conversion factors, we want to use the inches on the bottom there as our conversion factor. And this is how you should show it. 12 inches on the bottom, 1 foot up on top. Inches divided by inches would cancel. We will multiply 453.6 times 1 and hit equals, divided by 12. And we will end up with 37.8 feet. Yeah. So let's talk about a couple of things here. First off, let's talk about significant figures. Is my answer the correct number of significant figures? How many significant figures should it have? Should have 4. And the reason it should have 4 is when we look at this conversion factor here, this is a English to English conversion factor. Yeah, 12 inches is 1 foot. When you have an English to English conversion factor, you have a metric to metric conversion factor. They are considered exact numbers, which means we don't have to worry about them in this calculation. This is considered an exact number, which means really the only number that we have in this calculation where we're doing nothing but multiplying and dividing is the first number, which does have 4 significant figures. My answer that I wrote has only 3 significant figures. So technically speaking, we actually would need a 0 there, right, to get us the 4 significant figures. Doesn't change the meaning of the number, right, but does give us the proper number of significant figures. You could also do scientific notation if you really wanted to as well. We do end up with feet. So if you have an equality that is a English to English, metric to metric, it is considered an exact number. When you cross over from English measurements to metric measurements, you do have to look at the significant figures in those conversions because they are not exact. There is one or a few that are considered exact. The one that you come across the most that is considered an exact is 1 inch is 2.54 centimeters. That is a crossover sort of unit, but it is considered an exact value. So you would not look at it. But pretty much it's a safe bet to look at ones where you do cross over English to metric. I will also say probably 9 times out of 10, even though you might have to look at one of those conversion factors in your calculation that is that crossover one, it still is almost is a lot of times still that first number that is the right number of significant figures, but you should technically look at it. So for example, if you had like 1 pound is equal to 454 grams, that is English to metric, that you should look at the significant figures in that conversion factor if you used it. Which number should you look at, the 1 or the 454? You should look at the 454. So in a crossover sort of guy, you always have one number that is 1 and some other number in that, and you should always look at the other number. So if we had this in a calculation, technically that would be 3 significant figures, and we should take that into account when we're doing our calculation. Again, in a lot of cases, you'll still be okay in that case. Question on that there. So again, if we had, let's say we had 1 mile equals 1.6093 kilometers. And let's say that I was driving, why not? We were driving a safe and respectable 45 miles per hour. What would be my speed in kilometers per second? Take a moment and see what you come up with. Okay, let's take a look. So we basically have a couple conversion factors that will hopefully get us there, or equalities that will get us there. From the first one, we could write 1 mile, right, over 1.6093 kilometers. Our 1.6093 kilometers is 1 mile. Once again, you don't use both of them in a calculation. Otherwise, you undid what you did. This is an hour is 3,600 seconds. By the way, there's how many seconds in a minute? There's 60 seconds in a minute, yes. And there are how many minutes in an hour? 60. Right. And in one day, there's how many hours? 24 hours. Sometimes people go 60 on that one. I don't know, but you know, so they go 60, 60, 60. So by the way, this might not be provided for you. There are some things that you should hopefully know, I hope. Yeah. So from the other one, if you wanted to cut through that, you could also use these if you chose to do so. You could do 1 hour over 3,600 seconds, or 3,600 seconds is 1 hour. These are our conversion factors, right? All right, so whenever we have any type of unit, right, something per something is basically 2 units. It's really a fraction. Typically, the number always stays with the first unit, and the other guy is basically 1. So basically, if we were to set this up dimensional analysis way, we got 45.0 miles over an hour. We basically going to need to convert the top guy into kilometers, right? The bottom guy into seconds. You should write it like this so you can clearly see where the units are. I'm going to start with the miles. So by writing it like this, I could clearly see that the miles are up on top, which means if I want to get rid of the miles, I should use this conversion factor as it is opposite, 1.6093 kilometers per a mile, right? At this point, the miles will cancel, and I'm in units of kilometers up on top, right? And hours on the bottom. I am good on top. I now need to convert the bottom guy from hours into seconds. By writing it like this, I should hopefully clearly be able to see that the hours are on the bottom. And that means to get rid of the hours, I need to use the one where hours are up on top, which is opposite, which means 1 hour is 3,600 seconds. At this point, the hours will cancel. The units that I am left with now are kilometers up on top, seconds on the bottom. The reason you should do it like this, besides that is what you're supposed to be doing in chemistry, is setting up like this, is I can't tell you how many times I've seen people do this type of calculation, and they put like the seconds up on top and the minutes up on top. So they end up dividing or multiplying when they should divide. It's a very common mistake. So you do need to show your work, and this is what it means by showing your work, showing the units here. To do this, what we're going to do mathematically, once again, is just multiply anything that is up on top and then come back and divide by whatever is on the bottom. So that is mathematically what we're doing. So in this case, we're basically going to take 45 times 1.6093. We're then going to hit equals, divided by 3,600. And it's going to give us a number that looks something like this, 0.0201165 kilometers per second. So first off, any question on the number? We're going to clean it up here in a second, but any question on that? Now, I will say this as also a note that sometimes people screw up punching these things in their calculator because they want to punch all this stuff in at once. And if you do not know how to do that correctly, I would highly recommend you do not do that if you do not know how to use parentheses correctly, because your calculator will give you the wrong answer. The safest thing to do, for example, is as many numbers as you have up on top. You can multiply as many numbers as you like on that. You should hit equals at the end. Then come back and divide by the first number on the bottom, hit equals. Divide by the second number on the bottom, hit equals, and you will be in good shape. You will usually always get the right answer. What happens sometimes if you have multiple numbers on the bottom is people want to put it all in at once, don't put the parentheses correctly, they end up with the wrong numbers. So it's a really good idea to multiply as many as you want on top, divide each of the bottom numbers by the bottom, individually hit equals. Don't be afraid to hit equals along the way, and that should help you. Also, if you're doing a multiple step type of problem, you can do them in parts, get an answer after the first conversion, do the next conversion. If you do it sort of in piecework, you should again avoid rounding until the very end, so you don't sort of mess up the number. So let's take a look at what we should evaluate here in terms of significant figures. This should I evaluate? That is going to be a measured exact number. That's going to be a exact number. Yes, seconds and hours is all the same. Don't have to worry about that. Should I look at this conversion factor? The answer is yes, you should. It is English to metric, right? Kilometers is metric, English is miles. This number that we would look at would be this number right here, which has how many significant figures? 4, right? Or 5, if I could count. Yeah, it's kind of like 4, but 1 extra, and they're for free. So that is 5 significant figures. The number here we should definitely look at has 3 significant figures. That means that the answer should end up with 3 significant figures. And that takes us to here in terms of our answer. That is this number right here is our 3rd significant figure. All those zeros at the beginning are not significant. So we start counting at the 2, the 0, and the 1. That means we should end up with 0.0201 kilometers per second. Yeah. Also, obviously, you could do scientific notation of something like 2.01 times 10 to the minus 2 kilometers per second if you want to do scientific notation. Any question on dimensional analysis there or showing that work there? For credit in this class, yes, you need to show the calculation like this on the bottom. Yeah, you don't necessarily have to write out the equalities or the conversion factors, but you do need to show the dimensional analysis where the units are canceling each other. That is work. Numbers scribbled on a page is not work. Yes. Doing the stacking method, I like to call it, where you go like 35 meters per second, divided by 4 or 5 feet per minute, and you lose track of what you're doing here. That is not the correct way to show it. So you do need to show it this way to receive credit, the setup, and then obviously the answer to the proper number of significant figures. Any questions on that there? So let's talk about another conversion here. Why don't you try this one here? Let's say we did some measurements and we had 23.6 cubic feet. And I want to know how many cubic centimeters that was. See what you come up with. We'll give you some conversions. 1 foot is 12 inches. 1 inch is 2.54 centimeters. All right, see what you come up with. Okay, let's take a look. So in this case, we want to go from cubic feet to cubic centimeters. And we could use our normal kind of conversions here. So we'll start with our 23.6 cubic feet. Really, cubic feet are up on top. That means to get rid of it, we do need to go put the feet on the bottom. And that would be 1 foot is 12 inches. Will that completely cancel out my cubic feet? It will not. I want to get rid of 1. We technically have to do this not once, not twice, but technically you need to do this 3 times to properly cancel that out. Feet once, feet twice, feet 3 times is cubic feet, cancels out the cubic feet. Up on top now, inches times inches times inches is now inches cubed, right? Any questions on that there? That means I now want to go from inches cubed to centimeters cubed. I could use this conversion. Inches, as I can see, are up on top, so we do want inches on the bottom. 1 inch would be 2.54 centimeters. Once again here, that's only going to take care of one of them, so we do technically need to do it 3 times here. And that will take care of our other inches here. That leaves us centimeters times centimeters times centimeters, which is centimeters cubed, which is what we're looking for. We're going to multiply everything on top, divide by the bottom. Doesn't look like there's much to divide by, so we're just going to multiply times 12 times 12 times 12. looks like you get something like 6.8277.5796 on your calculator. This would be cubic centimeters. In this case, that is an exact number all the way through there. These are also exact numbers, which means in like most cases, if you're just doing a conversion, usually that first number is probably the right. That is 3 significant figures our answer should have, which takes us to here. That means we should end up with 668,000. Do I put a decimal? I do not, otherwise that's more than 3, right? This would be cubic centimeters. You obviously could also do scientific notation if you wanted to as well. And that would be something like 6.68 times 10 to the 1, 2, 3, 4, 5. Looks like, yeah. Yeah. What did I put in my calculator to do that? We're just basically multiplying everything that's on top. So basically everything across on top gets multiplied. Any numbers, if we had any numbers, they're all 1, so you really don't have to divide by it, but they're all, whatever numbers are on the bottom, you would divide by. Other questions? Now you could absolutely, if you wanted to, show the work like this. Although I might not recommend doing it, and I'll tell you why in 1 second here. You could do it that way. The reason I would not perhaps recommend doing that is I can't tell you how many people never actually do that 3 times. They do the units, but they never actually do the number part. So it's a very common mistake when people write it like that. They actually forget to do the math part of it. They will kind of fix the units, but not really the number. So sometimes it's better maybe to write it out so you could see that you need to do it that many times. But if you remember to do it, you could absolutely, obviously set it up like that. Question on that type of conversion, which sometimes confuses people. Yeah. Yeah, as long as you show some type of work that shows that you basically has to cube it or do it 3 times, it's fine. Yeah. Other questions? Now, speaking of units, though obviously we use that. There are some, obviously, some equalities and conversions that we use a lot. The different types of units, right? There's length, right? And very commonly, meters is a common unit, centimeters, kilometers, millimeters are common units that we use a lot. There's 100 centimeters, right? And 1 meter. There's 1,000 meters in a kilometer. Mass, very common units of mass are grams, kilograms. Those are usually very common units that we use a lot, milligrams occasionally. There's 1,000 grams in a kilogram, the common one. Volume, right? Units of milliliters, liters, cubic centimeters are used a lot. There is 1,000 milliliters and 1 liter is used a lot. A milliliter is the same as 1 cubic centimeter. And if you're in sort of healthcare or like a medical show when they say give them 5 cc's, that is also a cubic centimeter. Cc is sometimes used, but this is a relationship that is used a lot as well. How do we get to something like a cubic centimeter? It's kind of like what we just saw. If you took the length of something times the width times the height, and you did 3 different length measurements, centimeters times centimeters times centimeters, that gives us a cubic centimeter that is a volume. So a lot of times, especially with a cube, if you kind of cube the length measurements, that represents a volume. So that's why what we saw there, cubic centimeters, is actually a volume. Each of these individual measurements, those are all length measurements, right? Obviously, temperature for the most part, as we talked about, Kelvin is, again, the one that we use the most. Again, degrees Celsius does obviously come into play a lot as well. And time, seconds, hours, days are used a lot. Any questions on any of those units, dimensional analysis, how to show all that? Okay. We talked about earlier, again, you know, the 10 to the -2, for example, is centi. that is 1 centimeter would be 10 to the minus 2 meters. So you'd want to, again, make sure not to get those things backwards. We get, by the way, this conversion up here by dividing both sides by 10 to the minus 2. Gives us 100 centimeters is equal to 1 meter. So again, that is how we could get those. When you do any type of conversion problem, you can do it different ways depending on what conversion you take, as long as they are legitimate conversions, not ones that you make up. You should end up with the same answer regardless of what pathway. So there are some different pathways, obviously, as you do a conversion problem, but they all should really end at the same spot if you sort of choose it correctly. Any questions on any of that there? Okay. Last thing we're going to talk about here then, the kind of this pre-chapter is density. And density is the really the mass of a substance to its volume. And common units of density are typically grams per milliliter or grams per cubic centimeter. And those are the typical units that you find in solids or liquids. For gases, as we will see when we get to the gas chapter, a lot of times density is given in grams per liter. So when we do get to gases, that's the typical units that you see there for gases. Once again, obviously that conversion we just saw, that 1 milliliter is the same as 1 cubic centimeter. It's basically the same thing as you get it. Density is mass divided by volume, which means if you rearrange that equation, because you could solve for any of those three things, volume would be mass divided by density, and mass would be volume times density. Sometimes people remember the DMV triangle. Density is mass divided by volume. Volume is mass divided by density, and mass is density times volume, right? It's the way to do that. Now, in terms of the volume part of it, we could get volume in a couple of different ways. We could get volume, obviously, by just simply reading the volume, right? The meniscus. We could do what we just talked about. If you have maybe a cube or something like that, you could use a ruler and take the length times the width times the height, and you could get the volume that way. Probably the most common way or that we get volume and density is what's known as volume by displacement. And basically what that means is if you take a solid sort of object and you put it into a liquid, such as this, when we put it into the liquid level should rise, right, as the solid goes in. And basically our initial volume to our final volume, if you take the difference between those two, that is the volume of the object. So the object will displace a volume equal to its own. And that's a very common and easy way to figure out the volume of a solid object. Just basically drop it in some water and take a before and after volume reading, and you can do that. The units here of density, grams per milliliter, means that the units stay, and that means they do not cancel out. So you should have 2 units. It should always be however many, the number should stay with the grams part, and it should be 1 milliliter or 1 cubic centimeter. So let's just say we had a metal with a density of 1.32 grams per milliliter. How many pounds of the metal are there if it displaces, we'll do, actually we'll do water from 23.5 milliliters to 28.6 milliliters in a graduated cylinder. All right, see what you come up with here. Again, there's 1 pound is 454 grams. Let's see what you come up with. Okay, let's take a look and see this particular one. So it's kind of very similar to what we just talked about, be the volume by displacement. So we got some water. It is 23.5 milliliters. We got this solid guy here that has a density of 1.32 grams per milliliter. We're going to toss it in. Once it goes in, obviously we should see an increase in the size of the beaker. No, I'm just kidding. And the 28.6 milliliters is where it should go. So if we think about density, which is mass divided by volume, obviously we have the density given to us. We do have the volume given to us. So obviously it would make sense to solve for mass, since that's the only thing we do not have. And since we are looking for how many pounds, which is a mass, that is a good route to where we want to end up. So volume times density here. Now, to figure out our volume here, it would be our final volume, which was 28.6 minus our initial 23.5 milliliters. And that's going to give us a 5.1, I believe, milliliters in this case as the volume of the object. So now we have the volume, we do have the density. We could also use the density as a conversion factor. So you can say, for example, 1.32 grams over a milliliter, or you could say a milliliter is 1.32 grams. That allows us to, if we wanted to, do this problem more of a dimensional analysis sort of approach, where the mass would be our volume of 5.1 milliliters. Here again, we could clearly see milliliters are up on top. So we do want our milliliters on the bottom here. And our milliliters here will cancel. We will end up with 5.1 times 1.32 gets us 6.732 grams. That is close to what we want, but we do want it in pounds. So we could use, again, this equality and a conversion factor to do so. Once again, setting this up more of a dimensional analysis approach. Grams are up on top, so we do want grams in the opposite location, so it cancels, and we would have 1 pounds up on top. Again, here we are multiplying the top, dividing the bottom. That's what we're doing. Same thing as what we did here, basically multiply and divide by 1 in that case. We would take that divided by 454, going to get us a 0.014828194 pounds, which clearly is too many significant figures, right? This should end up at how many sig figs? Should end up at 2 significant figures, which would take us to here. We would look at the 8 and we would round up in this case to a 5 pounds. It is 2 significant figures really off of the first calculation we did, right? The subtraction. We would go to decimal places, which is 1 decimal place, but gave us 2 significant figures, which we carried over here to our multiplication step of 2 significant figures times 3 significant figures, which means technically speaking, this number should have ended up with 2 significant figures if we rounded at that point. And obviously here, 2 significant figures is less than that, and we should end up with our 2 significant figures here. Any questions on that calculation there? Density, obviously, if something is more dense than water, right, it will sink. If something is less dense than water, it will float. If we have liquids at different densities, what happens when we put them together? They will separate out, yes? And the most dense liquid would be down here. And least dense would be up here. And if I threw something in there and it got stuck right there between those 2 layers, that means that that thing is less dense than what's below it, right? And more dense than what's above it, right? Because it's sunk at that point. Any questions on that or density? All right, that should wrap up the pre-chapterness here.